All right, welcome everyone to our session after lunch. And as you'll be all fully aware, there was an announcement about wearing masks. So I think they're being supplied and already people have them on, so that's great. So we have two speakers, and to get away on time, we have Clayton Butterley, who's going to talk to us about optimising nitrogen recovery from livestock waste for multiple production and environment benefits. And Clayton has come up from the University of Melbourne, so I'll hand over to you, Clayton. Thank you.
Thanks, Tim. So my presentation today was meant to be summarising the research progress on a CRCP project titled Optimising Nitrogen Recovery from Livestock Waste for Multiple Production Environment Benefits, and unfortunately our industry partner had pulled out during COVID. But nevertheless, the research group has soldiered on, and we've been doing a number of studies in the laboratory and otherwise, and I'll summarise those today. So firstly, I'd like to acknowledge all my co-authors in this, and many of us are here at the conference, so I encourage you to come and have a chat with us. So today I'll go through this project and this research work. The University of Melbourne group as a whole has quite a focus on nitrogen cycling in agricultural systems, and more recently nitrogen from livestock waste has become a bit of a brief. I'll summarise some of the research activities and outputs, as I said before, and hopefully have you on board with our overall aims to develop cost-effective management of livestock waste for enhanced environment and productivity benefits. So we know that recently there's always been quite a push for reusing nutrients from agricultural waste and animal manures, but more recently there's a lot of internet traffic around applying sort of the economics framework of a circular economy to agricultural systems and nutrient cycling, whereby nutrients from animal systems, predominantly manure, are returned to the land and used to produce food, thereby reducing the reliance on synthetic nitrogen fertilisers. And obviously for the people in this room, we're all very well aware of they're not only a valuable source of nutrients, but they're also a very valuable source of organic matter for soils. And I'd say that in terms of domestic waste and green waste, we're doing a fairly good job. This is an in-vessel composting system just out of Brisbane. You know, we're doing a really good job at recycling the organics from domestic systems, because there's sort of a waste management drive there of getting the materials out of the system and out of the cities. But for agricultural waste, particularly intensive confined animal feeding operations, I'd say that we're not doing as well as we probably could. And invariably most of the manures that are generated, and we heard from Wendy Quaid in the previous talk that, you know, the increasing animal production, intensification of agricultural systems, and the amount of waste that are becoming available, and particularly for chicken meat, the consumption is increasing. And I feel like we could probably do a lot better at reusing and recycling the nutrients within our agricultural food systems. So if we just use the poultry as a bit of an example there, even though I'm saying that we could reuse and recycle the nutrients from the end products, by the time we collect the waste materials, most of the nitrogen has already been lost. And so the focus of some of the research here today is to see, well, how can we take a step back and try and increase the nitrogen concentration in the livestock waste. So in the chicken system here, The birds are raised on bedding. Birds excrete uric acid. It's rapidly hydrolyzed to urea, then forms ammonia. And we know that this occurs because the sheds are actively ventilated and that ammonia gas is pumped out into the surrounding atmosphere. So looking at the ABARES numbers for 2021, there's about 678 million chickens produced in Australia, and doing some rough calculations for the emissions of around 11.7 grams per bird, we can work out that there's probably around 8,000 tonnes of ammonia produced per year, and the average number of farms there could be maybe around 1.9 tonnes per shed, 10 tonnes per farm. So not a lot of nitrogen if you consider that we are using around 1.8 million tonnes of urea in Australia, but there's certainly a valuable nutrient source and a hotspot of nitrogen in the environment. So the group, led by Delhi Chen, has produced a couple of field experiments, 2015-2016, whereby they introduced lignite into intensive feedlots and showed that ammonia emissions were reduced by about 66%, and another study done on our Dookie farm by about 30%. So lignite has a low pH, high CEC, has a fair bit of dissolved organic carbon, and these are the sort of the mechanisms by which this is thought to have reduced the ammonia losses. But Bing's talk earlier this morning in this same session highlighted that it's nice to think we can put lignite into animal waste streams, but the lignite has a high water concentration or water content, and in most cases it's not appropriate or economic to move this around. So just summarising Bing's work from this morning there is that, heating the lignite at around 200 degrees shows that you can dewater the lignite, and I guess the overall aim is to not reduce its absorption capacity, but in fact the paper there shows that you can enhance that ammonia absorption capacity. And I guess I'll just highlight the fact that the relative differences between moist air and dry air show that humid air and water films and the moisture within the litter is and the lignite, there is quite important for capturing that nitrogen. So yes, we can dewater the lignite, it works really well, but in fact all the lignite's in Victoria, and we heard this morning that over about a quarter of the world's lignite is in Victoria. And certainly animal production systems are not co-located with that lignite. So some of the work which Bing did touch on this in the end of his talk was to see whether or not we could get black coal and modify the surface properties of the black coal to behave like lignite. And that's been a predominant focus of Wei in her PhD. So he also showed this picture, which basically shows that using a simple air oxidization, you can increase the surface functional groups, particularly the acidic functional groups, and these are binding ammonia. So working on from this then is to take that those modified products, so dewatered lignite, modified black coal, and seeing how well they perform in incubation studies with manures. So this one is by Wei Zhang, is about to be published soon, is one with cattle manure. So the lines at the top are the pure manure, and as you move down from that, the dark blue square there is black coal. You can see it performs quite poorly, and then the clump of treatments in the middle there are the modified and dewatered products. And so important thing to note here is that modified coal, dewatered lignite are performing equally or if the same as original lignite. So about half of the emissions that you get from the pure manure. So Brendan Costello in his PhD has been working with poultry litter predominantly, and he did a similar type study using broiler litter, and the numbers are pretty much the same. Reduce the overall emissions by about 50%, and modified black coal does relatively well compared to the original lignite. So I guess the assumed mechanisms by which this is occurring are predominantly the biological mobilisation. So there's introduction of soluble carbon, there's an excess of nitrogen, so the microbes are able to immobilise the nitrogen. We've showed you quite extensively about the absorption properties, and it was also thought that the lignite, which is quite acidic, would decrease the manure pH. And I guess those mechanisms are probably occurring, but I think the mechanisms are quite litter specific, and you know, in poultry litter, lignite actually reduced the soluble carbon, so a mobilisation process is a bit questionable, I would say. If we look at the absorption in solution doesn't really correlate with the reduction in emissions, and poultry litter certainly doesn't decrease in pH when we put these things in there. It's quite well buffered. So following on from that work, I guess, is so not only if we look at the emissions, but there's also other properties of the manure and the animal waste streams that are also quite beneficial. So we know that it's retaining in more nitrogen, so at the end we get a lot of more organic nitrogen retained. The material is dry mass loss is reduced, the material is breaking down slower, and this was consistent not only when you take pure poultry litter and add the lignite in, or when you get the materials and co-compost them together using an in-vessel composting system there developed by our PhD student, or postdoc now, Robert Impram. So consistently, high nitrogen content, reduced mass loss, reduced greenhouse gases and CO2 emissions, and an honours student is just taking out another experiment this week. Again, the time for the compost to reach stabilisation is always shorter. So it's quite good. And anecdotally, something that Brendan is going to follow up in his work is that you can completely tell which treatments are which. The lignite amended poultry litter has no odour and in fact smells quite pleasant. So I encourage you to go to his presentation on Friday. He will describe this system that he's designing with the intention of trying to investigate the influence of these additives on water potential and odour in poultry litter. So I won't give too much of that away. So I guess in summary, we showed across the board that we get higher nitrogen content with lignite, dewatered lignite and modified coal, but we really haven't had any opportunity to get out into the system yet to work out, well, okay, we've got more nitrogen then, but do we lose it during subsequent processing, co-composting or application to land? We're not really sure about this retention pipeline. And I guess ultimately we need to get that nitrogen back into a plant if it's going to be any benefit. So that also is not tested at this stage. So yeah, most of the work we've done at the moment is all in the lab and glasshouse, so we'd love to get out into commercial broiler farms. And just to re-emphasise, our overall goal is really about improving nitrogen efficiency in these agricultural systems with the ultimate aim, hopefully, of turning waste into some sort of valuable product or biofertiliser. So thank you very much, and yeah, I'd like to say that yeah, half of us are at the conference, so look out for us, say hi.
We got 1 minute for a question. Anyone have a question? I couldn't see any online. All right. Thanks, Luke. That was interesting. Thanks. All right. Our next speaker is Danielle De Rosa, and she is from Queensland University of Technology, and she will be speaking to us about optimising the use of soil organic amendments for improved environmental and agronomic outputs. Okay. So that concludes this whole session, I think. All right. Thanks, everyone.